So if you guys have your book, you can open up to the section that will start talking about this thing called neutralization reactions. And so we just went through precipitate reactions. We went through how you do that, how you predict if it's insoluble or soluble. Now we're going to look at something that's not a precipitate reaction, but an acid-base reaction. So we're on page 140, and that's kind of where the discussion starts. And we have what's called acid-base reactions. Okay, so for right now, we're going to have a real simple definition for an acid and base. Later on, it will change a little bit, but an acid is going to be something that gives off hydrogen ions. Okay, and then we got a base. It's anything that's going to give off hydroxide ions. Okay, and so if you remember, we had different types of acids. You guys don't have to rewrite this. If you want to, you can. But we have these things called strong acids. And the strong acids you have to memorize. So it is HCl, HBr, and HI. So on the periodic table, when you guys have your periodic table, it's not fluorine, okay? It's chlorine, bromine, and iodine. That would be your acid. So when you look at a periodic table where these things are located, it doesn't include fluorine, but it does include chlorine, bromine, and iodine. Okay, so that H's go with those. The other acids are going to be considered oxyacids, and they are HNO3, H2SO4, and perchloric acid, HClO4. So those are all strong. You have to memorize them. You have to have them down. Okay. So the other one would be nitrate, sulfate, and perchlorate with hydrogen. And what that means, do you guys remember what makes a strong acid have that characteristic? What would make it strong? So that when we put it into a container, if it's HCl, what do we know what it's going to do when we put it in a container? What do you think? So if I put 10 of them in the container, 10 HCls, what are they going to look like in the container? They're all going to be broken apart. 100% dissociation is what we call. So that would be 100% dissociation. I'm not going to write them all in here, but they're all going to be broken apart. Okay? That's what makes a strong acid. If it's a weak acid, so everything else is weak. If you know the 6 strong acids, everything else is weak. Every other combination is weak. Okay? If I put HF in here, and I put 10 of them in, then maybe not even one of these break apart, because most of them stay together as HF. It's kind of like a precipitate, but not having a precipitate. All right, if that makes any sense. That they all stay together, except for maybe one that would break apart. That make sense? So which one conducted really good? Strong acid. Which one was weak? Something like HF. Okay? It doesn't have anything to do with the concentration. Okay? Does that make it doesn't? They could be. This could be like 10 molar concentration, and this would be 0.1 molar concentration, or the HCl could be 0.1 molar. And this could be like a 10 molarity solution, which would be more concentrated, but it's still weak. Because the definition of weak means it dissociates or breaks apart less than 100%. The definition of strong, it breaks apart 100%. Breaks apart. All of it breaks apart when it dissolves. Okay, so that's a key. That's a real important key, because if you get that key down when you do these, they're going to make a lot of sense. Okay? A lot of sense. So, first thing I'm going to show you is the reaction. Okay? I'm going to show you acid-base reactions and what they're going to look like. And they're really simple. So, we'll do one, and we're going to do a strong acid. And so the key is strong acid. And we're going to put it together with a strong base. Now, what's a strong base? Is anything that's a metal hydroxide. So, strong base. Alright, so when we do the reaction, it's a double displacement. So this is aqueous. Okay, this is aqueous. We put them together. And we put them together, the front one switches with the K on the front here, and the K switches there. So it becomes H2O liquid plus KCl aqueous. Now, very rare occasion when you look at your solubility charts, you could get a solid out. I'll show you that here later this week. Okay, so this is just a double displacement. This is called a neutralization reaction. This is neutralization, what's taking place. Okay. And how do we know it's neutralization? Because we're making water, and water's neutral. No, so you're neutralizing the acid with the base. You're canceling out the strength of the acid with the strength of the base, and it's neutralizing out. Okay? So this is called the formula equation. Alright, so I'm going to clean this up a little bit. I'm not going to have the arrows going where they show the double switch. I'm going to go ahead and duplicate that so I can erase this little bit here. Okay, so we're going to have 3 parts to this just like we did precipitate. So why don't you guys break that apart but leave the water together. So go down through and show your complete ionic reaction. So show the complete ionic. They forget that, and they mess up. Either one, they don't remember what strong acids, the difference between a strong acid and a weak acid are. There's only 6 strong acids. And in the weak acids, they'll tend to separate those and act like they're a strong acid, which they're not. So, strong acid we break apart. So this is what it should look like on the what's called the complete ionic reaction. Any questions on that? Is that what you guys have? So now get rid of your spectator ions and write what's left over as your net ionic. So go ahead and write whatever's left over on your net ionic. Your chlorine and potassium cancel out because they're spectator ions, and what you're left with is H plus aqueous plus OH minus aqueous, and what you form is you neutralize those two. When you neutralize the two, you get just regular good old water. And neutral is pH of 7, and that's what you get, is a pH of 7 when they're perfectly matched. Questions on that? Okay, so that would be when we have a strong acid with a strong base. That's what it's going to look like when you do those type of problems. And you'll find out that they'll get really easy. If you know it's a strong acid and strong base, you already can tell that you'll have some spectator ions, and your final product could be H plus OH minus gives you H2O. Every time you get a strong and strong, that's what you're going to end up at the end. The H plus OH minus. Okay? So the second one we would do is neutralization reaction as well. So you don't have to read the title of this. Okay? And what we're going to have is going to have a weak acid paired with a strong base. Okay? And so there's a little bit of difference here. So I'm going to take a weak acid, take HF. I'm going to pair it with a strong base, NaOH. So go ahead, if you would, and just you guys go ahead and write out the products for that. Okay, we do the double switch. We get HOH, which is H2O. And we're left with NaF goes together. And if it has sodium in it, we know it's always aqueous, so that's what we got. Now, how is this different than the one prior? Okay, so remember, up here, we put HCl in, all of it breaks apart. So that's why we broke it apart. If we put HF in here, look, they don't break apart. Majority of them stay together. So when we do what's called a net ionic, or complete ionic, this stays together. Don't separate weak acids because they don't separate in the solution. You don't separate it out. Again, just to reiterate it, they don't break apart. They all stay together. Here, the strong acid, they break apart. So, I will say that 2 or 3 or 4, because this is the part that students want to break it apart, and you can't do that, or you're not supposed to. So but Na is a strong base, you definitely will break that apart, like we did before. We still form water, it stays together because it's molecular and it won't break apart. And what we're left with there is NaF, and that's aqueous, so that definitely breaks apart. questions you have on that? Now go ahead and write the final, what's called the net ionic. Cross out spectator ions. Only cross out spectator ions. Spectator ion is what occurs on both sides. It has to look exactly the same on both sides when you cross them out. Okay. So this should be your final result. Sodium is the only spectator ion, right? Can't cross out F because it's with HF. It's not that species of fluorine ions. So when you do a weak acid, you'll just have one spectator ion that you cross out instead of two. So that would be the result of that. Okay. All right, so I'm going to give some of these to work on. Again, they're not too difficult to do. Some of them, when you split them apart, they might be like H2SO4 or H3 something or CaOH2. You would still balance those out like you did before. So, okay. So I'm going to give you a couple of these to figure out. If you turn to page 163, C. I'm going to have you do 71 BC and 72 BC. 71 BC and 72 BC. On page 163, C.